All right, let's see what we took away from today's lecture. You definitely should have learned a lot of things about spring constants and springs, how they act in the structural system, but only you can really answer this. Also, the only thing that you can answer is what is the stuff that is not clear to you yet. So please go through that exercise and make sure that you come up with strategies that help you to really find more clarification about that. And let me know if I can help you with that. Last but not least, let's make sure that we understand our checkpoints here so that we can move successfully into our next lecture where we need this knowledge. So first of all, I definitely understand Hooke's law and I understand what a spring constant is and how that applies to the system. So I can definitely check that off. And because I understand this, I also understand the physical significance of a spring constant. That, for example, it takes, let's say, 100 Newton to stretch it 1 meter. That's the example we used. And you hopefully understand this and can check this off. And then you understand that the equilibrium conditions are really not different for spring problems. And you can calculate the forces in those spring cable structures, because it is just what we did in the last lecture with some add-on. So we understand that. And we can now, of course, use the stretch formula to determine the displacement or the stretch in a spring system. So today, very few checkpoints. They all very closely related to each other. But it's important that we have a solid understanding of that. So that concludes our summary page and what we took away. So let's move on and talk about the homework. All right, I believe we are very well prepared for our upcoming homework now. So let's take a look at each of the individual problems for which we're dealing with 2D equilibrium, including springs. And for our very first problem, you are asked to find the forces in these cables in BC and BD under the assumption that the spring AB is stretched by 250 millimeters. And keep in mind that this is given in millimeters, where this here is given in kilonewton per meter. So this value comes from your variable sheet. So please understand that these units need to compare to each other, so you have to do some conversion there. But once you've done that, you can calculate how much force is acting here, and you can then analyze how much force is acting in these cables. So it's kind of the reverse of what we've done in the lecture, just to solidify your understanding of Hooke's law and equilibrium in 2D. That means we can now move on to probably the most fun problem in this whole lecture series, which is this funny contraption here on the bottom. Let's first read the problem statement before I give you some visual and geometric pointers for this problem. So in the picture, each spring is stretched by 300 millimeters. So assume that these are already stretched by 300 millimeters. Before the stretch, the distance, the separation between point C and C and A was actually 2 meters. So H used to be 2 meters when the springs were unstretched. Now, the cable that wraps around A, B, C, and D, that cable here, had a total length, or does have a total length, of 4 meters. And that cannot change. It's a self-contained loop, if you will. And now, before I read on, also notice that we have these containers here, for example, the one here on the bottom left, that wraps around the pulley and then attaches to point B, which really pulls the system to the left, whereas at D, it pulls to the right due to gravity acting on these containers. And so that means it wants to stretch this diamond-shaped thing out, and therefore the spring here goes down and this spring goes up. And the problem is really for you to determine the mass in kilograms of each block to keep this system in equilibrium, under the assumption that each spring is currently stretched 300 millimeters. And keep in mind that here you read millimeters and here meters, just like before. You, of course, have to make that unit pure. Now, let's talk about the geometry of the system. So again, this cable here wraps around and that stays 4 meters long, no matter what you do to it. Also, please understand that there's technically some symmetry to this system. So, for example, I could divide the system in two And because it's symmetric, both containers, of course, have to have the same weight. So maybe I'm only going to care about one part of the system. For example, I can cut it like this, and I can only analyze whatever is going on in here. Don't get me wrong, if you make this cut that I drew with a solid line here, you will not come to a solution. It's not possible. But you can look at the individual nodes here, these ones, and you can, of course, calculate how much force the spring applies to this node. And be careful, because whatever this spring applies, of course, again, it's stretched, right? So it pulls up, and therefore that force is divided into this part and this part. But only this right side here really applies to this system. So I encourage you to think deeply about this. And once you understand what's going on at this node, you can move it down to this node, which then leads you to the weight in this container. And because the system is symmetric, this container is just the same as this container. I believe that should conclude the explanation for this problem. I wish you good luck with that. I'll be honest with you, it's not necessarily simple when you start with it, but I believe with the knowledge that we presented here in these lectures, you have all the tools you need to solve this. And if you have questions, of course, I'll be happy to help you through the discussion boards on Canvas. Good luck with that problem. It's a real fun one. All right, last but not least, we have a problem that is given in two versions. In its original state, I call this the unstretched state, so it's a little bit more faint. And then you have the stretched state. So that is this portion here, where you have the solidly drawn picture with the weight hanging on it. Let's read the problem statement real quick. Determine the mass in pounds of the cylinders, assuming that the sag S, so that's this value here, due to the cylinders is 0.5 feet. If the cylinders are removed, S is equal to 0. So this S would not exist. That's what this picture here is showing. Only if you hang the masses on there, you would actually create a vertical displacement. And yes, this is called S as well for sag, but please understand that this is different than the stretch of a spring. The stretch of the spring would be in line with the spring, and that is not what's asked of you here. We are looking for the vertical displacement. And that, of course, is different for each student depending on their variables or the variable combination of A and D. So please calculate that based on your individual numbers. But I believe that you can solve this with equilibrium and everything we talked about in this class. Notice, again, it's a symmetric system. So here you have K2 and K2. So both sides have equal stiffness and we have equal distance. Also, please understand that this length here does not change. Look that these are not connected here. So A and B are always apart by 1 foot, and that does not change no matter how much you pull it down. So in other words, you have a vertical, perfectly vertical displacement here because this cable keeps the springs in the same distance as long as the cable is in tension. And I believe that prepares us well for homework 3B, for which you study the equilibrium of particles, of course in 2D still. Please make sure that you develop a solid understanding of these concepts, because in our upcoming lectures, we will take this to the next level and talk about 3D structures and 3D structures with springs in it. My experience is that students are sometimes a little bit afraid of 3D analyses, but my goal in the next lecture is to show you that this is actually nothing to be scared of. If you have a solid understanding of what we talked about here today, you are definitely ready to move on. And I will show you how simple it can be to take this to the next level. I'm excited about that, about the upcoming lectures, because we can use that to analyze real life structures that we see in our everyday lives. And therefore, it's always more fun to apply it and to learn more about how the real world works. Until then, I wish you good luck with solving your homework. Stay safe. I see you in the next lecture.